Hi, welcome to Mathematical Fallacies. These are strange things in mathematics that come up, particularly in physics. So this is Extraordinary Concepts in Physics. I'm your host, Robert Ramapo, a professor at Michigan Technological University, and this class is being taught for credit at Michigan Tech. So you can find us on the web here. Search for Starship Asterisk and/or Physics X. And you can find us on iTunes just by searching iTunes. And here's the web address if you can read that. Good luck. Okay, so one of the things that I find really cool are mathematical fallacies, things that look true in mathematics but turn out to be somehow strange or somehow untrue. So when I teach occasionally mathematical physics to the graduate students at Michigan Tech, I put this particular one on the board and ask if people can understand what's wrong. When I first saw this, I just thought this was the funniest and coolest thing. I just thought this was great. So I teach this not only because it's fun, but because when I teach math physics, usually maybe once a semester or so, somebody makes a mistake just like is made in this particular quote, proof, unquote. And also I've seen some of the other mistakes here. And also, one of the ways I learn is by studying things that interest me. So if I understand the mathematical fallacies, it helps me understand math better and helps understand the math that underlies the physics better. Now this isn't so, we're not getting into really the deep math here. This is just sort of fun stuff. You just need to know algebra, a little bit complex variables to know this. So it's just fun. So we'll start out with A equals B equal to 1 in this proof. And then we will we'll multiply both sides by A, which will give us A squared on this side and AB on that side. And now we're going to subtract B squared from both sides. They both get B squared if that's equally fair. Now you might notice that A squared minus B squared can be factored into A plus B, A minus B. You can verify that by multiplying this out. A squared, and the middle ones fell out, and you get A squared minus B squared. The other side, we can just factor B out and get B times A minus B. Okay, now we can cross out the A minus B's and get A plus B is equal to B, and now we can add them up because we said they were equal to 1, and we can show that 2 is equal to 1. So the way this works is that whenever you have any problem due that involves math in physics or math, you can first show this proof that 1 is equal to 2, then say that any number is equal to any other number, and then put down anything you want for the answer and say that this is mathematically equivalent to the answer to this problem, so I deserve to get full credit. However, your professor might not be so impressed, so it is best to know what's wrong with this. So many times people can guess, and the answer is that there was a step where you took out A minus B from both sides. So when you did that, A minus B is 1 minus 1, and 1 minus 1 is 0. So then you're dividing by 0. Now, sometimes you can get away with dividing by 0 and it doesn't matter. But this is a case in point that many times it does matter. And if you divide by 0, you're really doing a mathematically undefined operation, and just about anything can result. So in fact, 2 can be equal to 1. So the moral of the story for people doing lots of algebra in their physics or math is to be careful not to divide by 0. Or if you just can't get the answer, be sure to divide by 0 in the middle to get the answer, and then go toward the answer after that. Here's another one. This is actually probably even more common than the previous one. This proves that 2 times pi is equal to 0. So first we start out with x equals to 2 pi. Then we're going to take the sign of both sides. So the sign of x is the sign of x, and the sign of 2 pi, as we know, is the sign of 0. So now we're going to take the arc sine of both sides, and we get back with x, but now we have on the right side, we have arc sine of 0. Therefore, we get that x is equal to 0, because the sine of 0, as we know, is equal to 0. Therefore, the arc sine of 0 is 0. So x is 0. But wait a minute, we first declared that x is equal to 2 pi. Therefore, logically, one can say that 2 pi is equal to 0. So basically, all of trigonometry is meaningless. Geometry is taking a big hit here. However, there is a reason why this doesn't work, and this one might be easier than the other ones. The arc sine function is multi-valued. So the arc sine of 0 is not necessarily 0. In fact, it could be 2 pi. It's not clear what it is. So if you're doing a physics problem, you might need to find out what range the arc sine function would be. So you need to be careful. Arc sine is not the only ones. In fact, when I grade problems, Typically actually in introductory physics, the tangent function seems to be the big one. And quadrants of the tangent have to be carefully aligned that you don't jump between quadrants. Okay, here's one that comes up. X is equal to 1. That's the way a lot of these start. Let's take the derivative of both sides with respect to x. d dx is equal to d dx of 1. Well, the d dx of x is just 1. But when you take the derivative of constants, it's 0. So 1 is equal to 0. What's wrong with that? And the problem here, and actually there are times in physics problems where this is, people get away with this. Sometimes on purpose, sometimes not. But you can't do that really because x is not a true variable. So you need to keep track of what's really varying and what, like pi, is not varying, because you could just take the derivative with respect to pi sometimes and then all hell could break loose. So know your variables from your constants. Okay? Postulate the root of partial differentiation as well. Moving right along, negative roots. So we'll start with 1 equal to 1. How can that be disputed? 1 is equal to the square root of 1. We all know that. That's taught in elementary school for the first time you learn squares. So let's break up the 1 here is equal to, this 1 equal to minus 1 times minus 1. So now we're having the square root of two things that are multiplied, so we can separate them. So this would be the square root of minus 1, and this would be the square root of minus 1. So then we would have 1 is equal to I, because I is equal to, I is an imaginary number, which is equal to the square root of minus 1. So I times I is minus 1, so that 1 is equal to minus 1. So what's wrong with that? Well, by now you know mathematically is consistent enough to use. So this is a tougher one, and I have to admit when I looked at this I didn't immediately get this. This doesn't happen very often in practice. But it turns out that when you take the square root of x and y to be equal to the square root of, when you break it up into the square root of one times the other, that both numbers must be positive. So sometimes you have to check these little rules, and if it turns out not to be true, then you have to be careful. Okay, infinite series. Infinite series are cool. Most functions can be written as infinite series. Most numbers can be written as infinite series of other numbers. So here we go. One of the simplest infinite series is just declaring that 0 is equal to 0 plus 0 plus 0 plus 0, etc. Well, we can break each 1 up into 0 up into 1 minus 1, because 1 minus 1, we all know, is 0. So every time you see a 0, now replace it with 1 minus 1. So you get a long list of zeros equal to these things. So now we're going to regroup. We're going to take this one and break it off, the first one, and we're going to regroup these guys. And then we get that, can't see it very well, 1 plus minus 1 plus, minus 1 plus 1, but it's still that minus 1 plus 1, that too is also, sorry, I have to be careful about using the preposition to here, that also is equal to 0. And so all of these are going to sum to 0. But we're left with this guy out front, which is 1, so that 0 is equal to 1. How about that? Well, I won't quiz you on this one. The associative law cannot be applied to infinite series that are not absolutely convergent. So meaning the sum of the absolute values of each term itself converges. So if you take the absolute value of all these terms, you'll find that it diverges. So another little less known rule you have to be careful with. And coming near the end, this is a little bit, this is actually a more common problem, but the way it's demonstrated here is more complicated. So you can start with this equation, x squared plus x plus 1 is equal to 0. So then you're going to play around with this, and you're going to move the x plus 1 to the other side, and you get x squared is equal to minus x minus 1. And then you can divide by x and get x is equal to minus 1 over x. So you divided both sides by x here. And so now you have this equation, which is not really a solution, but you then plug that back into the middle one. That's what's happening. So you get that x squared minus 1 over x is equal to 0, x squared is equal to 1 over x, and x cubed is equal to 1. Therefore, x is equal to 1, because we all know that 1 cubed is equal to 1. So now that we have a solution, we can go take the solution and put it back in the initial equation. And we get that 1 plus 1 plus 1 is equal to 0. But we all know that 1 plus 1 plus 1 is equal to 3. So here we're not just showing that 2 is equal to 1, we're showing that 3 is equal to 0. So the question is, what went wrong? Well, this is a little more complicated, but I think many people might already have a guess. And the guess is that the problem is really in this step here. So although x is equal to 1 is only one solution, x cubed is equal to 1 actually has 3 roots. And it is really the other, at least one of the other roots that is the real solution to the problem. And the x equal to 1 is actually an extraneous solution. Many times you can get a solution in physics and it's called not physical. Because if you put it in, it turns out to be outside the range of what's going on in the problem. Well, sometimes extraneous solutions can be not mathematical as well. They're not even general solutions to the problem. You got off on a different branch of a cube root or even a square root and didn't come back to where you wanted. So the moral of the story is be sure your solution is a real mathematical and physical solution. Otherwise, anything can happen. And with that, I'll wrap up mathematical fallacies and remind you to keep Schrodinger away from your cat. See you next time. Particularly in physics. So this is Extraordinary Concepts in Physics. I'm your host, Robert Nemroff, a professor at Michigan Technological University, and this class is being taught for credit at Michigan Tech. So you can find us on the web here. Search for Starship Asterisk and/or PhysicsX, and you can find us on iTunes just by searching iTunes. And here's the web address if you can read that. Good luck. Okay, so one of the things that I find really cool are mathematical Hi, welcome to mathematical fallacies. These are strange things in mathematics that come up